Welcome to InfoSec Bytes, your go-to podcast for bite-sized insights on information security, AI, cloud, quantum, and cybersecurity incident root cause analysis. With over 100 episodes, we've got you covered on the latest trends and tips. This year, we will focus more on cloud computing, along with other topics, so stay tuned. Please like, subscribe, and share to join the conversation on various platforms: Spotify, Apple Podcasts, YouTube, Amazon Music, and stay secure.
It's really fantastic to be jumping into this one today. I mean, we have an incredibly dense, highly technical, and honestly a very urgent architectural problem to unpack.
Yeah, we really do. And look, if you are a cloud architect, a GRC analyst, or an auditor listening to this right now, I want you to, pause for a second. Think about your day-to-day operations. You already know the absolute nightmare of proving that cloud data is actually deleted.
Oh yeah, the compliance headache.
Right. It is arguably one of the hardest things to guarantee in any modern distributed infrastructure. So today's mission for this deep dive is critical. We are looking at a massive stack of high-level research detailing a huge collision course.
A very precarious gap, really.
Exactly. On one side, we have cloud data sanitization, specifically a technique everyone relies on called crypto shredding. And on the other side, we have the impending and frankly terrifying post-quantum cryptography era, or PQC.
And we're going to see how these two unstoppable forces are basically about to collide in your environments. Because when we look at the research, we're really examining the bridge between today's incredibly strict compliance frameworks. I mean, think GDPR and its right to erasure mandate.
Right to be forgotten.
Exactly. We are bridging those strict mandates with tomorrow's quantum realities. Realities that threaten to completely undermine the cryptographic foundations we use to actually achieve that compliance.
So let's start with the fundamental architectural shift that makes all of this necessary in the first place: the physical reality of the cloud. Because it makes traditional data deletion essentially impossible.
It really does. I mean, think about the old on-premise days.
Right. If an auditor demanded proof of deletion, you could physically pull the hard drive from the storage area network, run it through an industrial degausser.
Or just take a drill to it.
Yeah, literally drill holes in it and hand them a certificate of destruction. But in AWS, Azure, or GCP, that physical control is completely out of your hands. You cannot walk into a hyperscale data center with a magnet.
No, the security guards would have a serious problem with that. And that abstraction layer is the root of the entire data sanitization dilemma. When a user issues a delete command in the cloud, the provider's storage controller isn't immediately zeroing out the physical sectors on the underlying solid-state drives.
Because that would be terrible for performance.
Exactly. It would be incredibly inefficient from an I/O perspective. Plus, it would drastically reduce the lifespan of the flash memory.
Because of the wear leveling algorithms, right?
Right. SSDs use wear leveling to make sure degradation happens evenly across all the flash cells. If the controller actually tried to overwrite a specific file with zeros, the flash translation layer would likely just write those zeros to entirely different fresh cells anyway.
And it would just mark the old cells containing your sensitive data as garbage to be collected later.
Exactly. So instead of doing all that, the provider simply deletes the pointer to that data in their metadata plane.
So the metadata pointer is gone. To your application, the database row or the file appears deleted. But the actual ones and zeros are still sitting on those shared physical disks.
Sitting right there in plain text if you didn't encrypt it.
And this is what we call residual data. It just sits there completely invisible to you until the cloud provider's storage systems eventually, randomly, overwrite those specific physical blocks with new customer data.
Which could be minutes or it could be months.
Right. And I want the listeners to really visualize their own environments for a second. Have you ever been tasked by legal or compliance to hunt down and completely purge a single user's personally identifiable information?
Just finding it is half the battle.
It's bad enough on a single legacy on-prem server. But try doing that across multi-region active databases. Try doing it in S3 buckets where you have versioning turned on.
Well, versioning is a nightmare for deletion.
Or across immutable backup vaults that were explicitly engineered by you to prevent data from being tampered with or deleted. It's an absolute archaeological dig.
And that dig introduces massive friction. It's not just a headache for your data engineering team, it is a severe compliance risk. As long as that residual data exists on the physical media, it remains potentially accessible.
Accessible to who, though? The hypervisor isolates tenants.
Generally, yes. But what if a sophisticated adversary finds a zero-day flaw in the hypervisor, or a bug in the storage controller's isolation mechanisms? If that boundary fails, your residual data is just sitting there.
Which brings us to the really elegant solution that the industry adopted to solve this exact problem. Cryptographic erasure, commonly known in the field as crypto shredding. Time for a quick host note here, because we're going to look at this from a deep architectural perspective, not just a textbook definition.
Right.
Crypto shredding is the process where, instead of trying to overwrite physical storage media that you literally do not control, you deliberately destroy the cryptographic keys that protect the data.
You target the key, not the data.
Yes. By permanently purging the key material, the ciphertext left behind on those shared disks is instantly rendered completely undecipherable.
It represents a brilliant paradigm shift in how we handle data life cycles. I mean, instead of playing whack-a-mole, hunting down every single replicated copy, snapshot, caching layer, and application log file containing that sensitive PII.
Because it always leaks into the logs.
Always. Instead of doing that, you changed the architecture at the ingestion layer. You encrypt the data the absolute moment it enters your environment. You centrally manage the key used for that encryption in a hardware security module or a cloud key management service.
And then, months or years later, when a GDPR right-to-erasure request comes across your desk, you don't even touch the data. You execute a cryptographic kill switch.
You destroy the key.
I've always loved the conceptual simplicity of it. I usually explain it to non-technical stakeholders, like the legal team, like this. It's like locking your house, throwing the only key into an active volcano, and then pouring 50 feet of solid reinforced concrete over the entire property.
That's a very vivid analogy.
But it works. The house is technically still there. The data is still sitting on a flash drive in an availability zone somewhere in Virginia. But nobody, not even you, is ever getting inside again. The residual data problem is functionally solved.
Functionally solved, yes, but heavily, heavily regulated. From a GRC perspective, the research highlights that regulatory bodies don't just take your word for it. You can't just click disable on a key in the AWS console and call it a day and tell the auditor you're compliant.
Oh, I wish it were that easy.
We all do. But according to stringent standards, and the research points specifically to NIST Special Publication 888 Revision 2 and ISO 27040, an organization has to rigorously document the entire cryptographic lifecycle to legally claim valid data sanitization.
Okay, let's play auditor for a minute and unpack those strict rules, because this is where our GRC analysts listening really earn their keep. What exactly is NIST 888 Revision 2 looking for? When I submit an artifact to an auditor claiming I've crypto-shredded a database cluster, what granular details do I actually have to prove?
The burden of proof is incredibly high. First, you have to document the make, model, and version of the storage media.
Even in a virtualized cloud environment?
Yes, even then. You have to understand the underlying infrastructure. Then you must identify the specific media encryption algorithms utilized. For example, are you using AES 256 in Gallows counter mode? You have to document that and the exact key strength.
Okay, standard cryptographic inventory stuff.
But it goes deeper than that. You have to prove the mathematical integrity of how the key was generated in the first place. Did you use a FIPS-validated deterministic random bit generator? Was there sufficient entropy during the key creation process?
Let me stop you right there, because that entropy point is absolutely crucial. I see this misconfiguration all the time. If the random number generator used to create the encryption key was starved for entropy, which happens a lot in highly virtualized environments right after a system boots up, the resulting key might be weak.
It might be entirely predictable.
Right. If 10 virtual machines clone from the exact same golden image and boot at the exact same millisecond, they might have the exact same memory state. Without a hardware entropy source, they might generate the exact same random numbers.
Which means they generate the exact same encryption keys.
Exactly. And if the key was mathematically weak or predictable from the very start, destroying it later doesn't matter, because an attacker wouldn't bother trying to break the AES 256 encryption brute force. They would just mathematically guess or recreate your weak key.
That is a perfect distillation of the risk. Key generation is just the foundation, though. The research we are analyzing today specifically dives into the massive complexities of key wrapping.
Envelope encryption.
Yes, envelope encryption. In any enterprise-grade cloud architecture, you are rarely just generating one flat key for everything. You have a data encryption key, or DEEK, which does the heavy lifting of encrypting the actual gigabytes of files or database rows.
Because symmetric encryption is fast.
Right. But you have to protect that DEEK. So you have a key encryption key, or key, which sits securely in your key management service and encrypts or wraps the DEEK. When you want to achieve crypto shredding, you are usually sanitizing that key.
You destroy the master wrapper.
Exactly. And NIST requires you to document the specific wrapping techniques, the algorithms used for the wrapping, and their cryptographic strengths. Finally, you have to meticulously document your key sanitization technique.
Meaning, how did you actually delete the key?
Precisely.
Yeah.
You have to prove the exact hardware-level method used to zero out that key from the hardware security module's volatile and non-volatile memory so it can absolutely never be recovered.
Okay, so let's set the stage for the listeners. Let's assume the listener has built an incredibly robust, heavily audited, completely compliant process. They are top of their class, they are following NIST guidelines to the letter, they're using AES 256 for their data payloads, they are wrapping keys perfectly using envelope encryption, and they have automated the absolute destruction of the key encryption keys within a validated cloud HSM.
The auditor is happy.
The auditor is thrilled. The GDPR regulator is happy. You've got your compliance certificates framed on the wall. But here's the pivotal question that breaks this whole model wide open. What if the underlying cryptographic algorithm protecting the key exchange is fundamentally flawed?
And that question right there exposes the Achilles heel of the entire concept. If the algorithm protecting the data, or more specifically, the asymmetric algorithm protecting the secure transport and exchange of those wrapped keys, is broken crypto shredding is absolutely not equivalent to deletion.
It's useless.
To borrow your earlier analogy, it is like pouring 50 feet of concrete over the house, but leaving the back window wide open before you poured it. If the math fails, the entire compliance structure collapses.
Okay, let's unpack this. Because crypto shredding sounds like the absolute silver bullet for our modern compliance woes. We've relied on it for years. But here is where the research gets really interesting. And frankly, deeply unsettling for anyone managing long-term confidential data.
Unsettling is the right word. We need to address the quantum elephant in the room. Specifically, a highly aggressive, ongoing threat model known within intelligence and security circles as HNDL, harvest now, decrypt later.
Time for another host note for the audience because understanding the mechanics of HNDL is so critical to everything we're talking about. Harvest now, decrypt later is an active cyber attack strategy. Adversaries are stealing and stockpiling encrypted data today. Right now.
They know they cannot read it right now.
Right. They know it's encrypted with AES 256, but they are hoarding it with the explicit, calculated intention of decrypting it in the future, the moment quantum computers become computationally powerful enough to shatter our current encryption standards.
And it is vital to understand that this is not a theoretical whiteboarding exercise. This isn't academia. The research firmly indicates that well-funded adversaries, particularly nation-state actors, are executing the strategy at massive scale right now.
They aren't just breaking into corporate networks, are they?
No, they are positioning themselves at the backbone of the internet. They are utilizing BGP route hijacking to redirect massive swaths of encrypted cloud traffic through their own sovereign infrastructure.
Let me jump in on that because BGP hijacking is wild. For the listeners, imagine your data is supposed to go from your office in New York directly to your AWS instance in Virginia, but an adversary manipulates the border gateway protocol routing tables. Suddenly, your traffic is taking a detour through a router in another country for 5 minutes.
And during those 5 minutes, every single encrypted packet is mirrored and stored.
You barely even notice a latency bump, but they've captured the entire TLS handshake and the encrypted payload.
Exactly. They are tapping undersea fiber optic cables. They are quietly scraping misconfigured but encrypted S3 buckets. They are accumulating what intelligence communities refer to as frozen intelligence.
Frozen intelligence. It's a terrifying visual, honestly. They're literally building massive hyperscale data centers in their own sovereign territories for the sole purpose of storing petabytes of encrypted ciphertext. Just patient, silent storage. Waiting for the day that cryptographically relevant quantum computers, or CRQCs, finally mature.
It fundamentally alters how we have to calculate risk as security professionals. If we connect this back to your perfectly architected crypto shredding environment, if an attacker exfiltrates your ciphertext database backup, say, from misconfigured blob storage, and they also manage to capture your wrapped key material as it traverses the network during a TLS handshake today, what happens tomorrow?
If we connect the dots for the listener, this completely breaks the entire crypto shredding paradigm we just spent 10 minutes praising. If they have the ciphertext and they have the captured key exchange traffic today, Destroying your original key in your cloud key management service tomorrow does absolutely nothing to protect you.
Nothing at all.
You can zero out the HSM all you want. You can burn the data center down. The adversary already has a frozen copy of the locked door, and they have a frozen copy of the locked key. They're just waiting for a better lockpick to open it.
Precisely the issue. And the underlying math risk here is what makes this a ticking clock. Because the encryption protocols that secure our key exchanges and our digital signatures today, specifically asymmetric algorithms like RSA, elliptic curve cryptography, and Diffie-Hellman, they all rely on a very specific set of mathematical problems.
The hard math problems.
Right. Namely, the extreme difficulty of factoring incredibly large prime numbers or solving complex discrete logarithms. For a classical computer, even a massive cluster of supercomputers, solving these specific mathematical problems to derive the private key from the public key would take millions, sometimes billions of years.
It's computationally infeasible.
Exactly. But quantum computers do not process information linearly like classical computers do.
Right, they don't just process ones and zeros. They use qubits, allowing them to leverage quantum superposition and entanglement. They can evaluate vast numbers of possibilities simultaneously. And that brings us to the ultimate cryptanalytic weapon we found in the research Shor's algorithm. Let's dig into the mechanics of that, because I think people assume a quantum computer is just a really fast CPU that tries all the passwords faster.
That's a great distinction to make. Shor's algorithm isn't a brute force tool at all. It doesn't just guess passwords really fast. It is the highly specialized algorithm that exploits quantum interference to find the period of a mathematical function.
The period of a function.
Yes. And once a quantum computer running Shor's finds that period, it mathematically reveals the prime factors of the public key with shocking efficiency. It takes a problem that requires exponential time for a classical computer and reduces it to polynomial time.
Meaning it turns a billion-year problem into a weekend project.
Basically, yes. In practical terms, a sufficiently powerful, cryptographically relevant quantum computer running Shor's algorithm can completely break RSA or elliptic curve asymmetric key encryption keys in hours, or perhaps days.
So let's play this out for the architect listening. The adversary has your frozen intelligence. In a few years, they spin up a stable CRQC. They run Shor's algorithm against the TLS handshake they captured 3 years ago via that BGP hijack. The asymmetric algorithm, the RSA or the elliptic curve wrapper, crumbles.
Instantly.
They extract the symmetric key encryption key. They use that to unwrap the data encryption key, and suddenly your meticulously crypto-shredded, highly regulated GDPR data is sitting in plain text on an adversary server.
That is the exact sequence of events the entire cybersecurity industry is bracing for right now. If the asymmetric wrapper is broken, the strength of the symmetric AES-256 data payload doesn't matter.
Because AES-256 is actually quantum resistant, right? Grover's algorithm weakens it, but it's still largely safe.
Yes, AES-256 is generally considered safe from quantum attacks, but it doesn't matter how strong the safe is if the attacker just recovered the key to unlock it by breaking the weak transport mechanism.
Now, I know what a lot of listeners might be thinking right now. It is incredibly easy to dismiss quantum computing as a sci-fi problem for 2040 or 2050. It feels like something that won't happen during your current tenure, so why budget for it now? Why redesign your architecture today?
It's a common pushback.
But I want to challenge that mindset based on the research. We have to talk about confidentiality lifetimes. If you are securing data that only matters for a week, say temporary session tokens, or whether data HNDL isn't a huge concern, who cares if they decrypt a session token from 5 years ago?
Right, the token is expired, the risk is zero.
But what if your data has a confidentiality lifetime of 10, 20, or 50 years?
That is the critical metric. Think about genomic data, electronic health records, long-term financial audits, state secrets, or classified aerospace intellectual property. The value of that data does not expire quickly.
Exactly. If you are holding data that needs to remain secret for 25 years and it gets harvested by an adversary today, you are already out of time. The moment the quantum computer comes online, your data is compromised well within its required confidentiality lifespan.
The urgency articulated in the research is very real, and it is driving massive regulatory shifts right now. The research extensively cites the Cloud Security Alliance's Quantum Safe Working Group. They are not treating this as a distant theoretical threat. They have established a specific target deadline, colloquially known across the industry as Q-Day.
Q-Day. Like Y2K, but with math.
Exactly like that. They have marked April 14th, 2030 as the date by which organizations absolutely must have their post-quantum infrastructure fully deployed and operational.
2030. Let that sink in for the audience. That is barely a few years away. In enterprise IT terms, where a massive Active Directory migration could literally take 3 years of planning and execution, a window of less than a decade to completely overhaul the fundamental cryptographic foundation of the global internet, that is a dead sprint.
It's going to be a massive undertaking.
So what is the lifeline here? How do we stop this harvest? Now, decrypt later nightmare and salvage the concept of crypto shredding before Q-Day arrives.
The lifeline the research focuses on is post-quantum cryptography, or PQC, and we need to differentiate this immediately from quantum cryptography.
Oh, that's the good point. People confuse those all the time.
Constantly. We are not talking about quantum key distribution or QKD. QKD requires specialized optical hardware, dedicated fiber lines, and shooting actual photons to detect eavesdropping based on quantum mechanics. It's hardware-based and incredibly expensive to scale.
You can't just run QKD on your laptop over a standard Wi-Fi connection.
Exactly. PQC, on the other hand, is entirely software and math-based. It involves entirely new cryptographic algorithms designed specifically to withstand cryptanalysis from both classical supercomputers and future quantum computers. Because it is math-based, it can run on our current classical computing platforms.
So your laptop, your smartphone, your existing cloud, virtual machines.
Yes, and it integrates directly into our existing protocols like TLS and SSH. We just swap out the math engine underneath.
Time for another host note on the specific math stepping up to save us. Because the research heavily features a standard called ML-Chem. That stands for Module Lattice-Based Key Encapsulation Mechanism. Standardized by NIST as FIPS 203, this is the algorithm that is officially replacing existing key establishment protocols like RSA and elliptic curve, Diffie-Hellman, to securely share secret keys over public channels.
The shift to lattice-based mathematics is fascinating, and it is a massive, massive departure from the crypto we've used for the last 40 years.
Right, because we're moving away from prime numbers entirely.
Exactly. Instead of relying on factoring prime numbers, which Shor's algorithm destroys, lattice-based cryptography relies on geometric complexity. Imagine an infinite multidimensional grid of points. That's a lattice. The underlying mathematical problem is called the shortest vector problem, or learning with errors. You are essentially given a point somewhere in this massive multidimensional space, and you are asked to find the closest actual lattice point to your location.
Let me try an analogy here to ground this for the audience, because visualizing multidimensional space is tough. In a two-dimensional grid, like a simple piece of graph paper, finding the closest intersection of lines to a random dot you drew is incredibly easy. You just look at it.
Right.
A three-dimensional grid, like a coordinate in a room, is a bit harder, but still simple for a computer. But when you scale that up to hundreds or thousands of dimensions and you introduce intentional mathematical noise or errors into the coordinates, the complexity explodes.
That's a really great way to visualize it. It turns out that navigating that multi-dimensional, noisy grid is incredibly difficult. More importantly, there is currently no known quantum algorithm, including Shor's, that gives a quantum computer any significant advantage over a classical computer in solving the shortest vector problem.
It doesn't have a period defined.
Exactly. It is quantum resistant by its very mathematical nature. And after years of intense global scrutiny and academic competitions, NIST has officially moved from the competitive evaluation phase to the final standardization phase.
Yes, the research details the fresh NIST standards that just dropped, and these are the FIPS numbers every architect listening needs to memorize. We have FIPS 203, which is the ML-Chem we just mentioned. This handles key encapsulation, which is how we securely negotiate symmetric keys over an untrusted network.
The key exchange.
Right. Then we have FIPS 204, which is MLDSA, or a module lattice digital signature algorithm. That one's designed to completely replace ECDSA for digital signatures, ensuring non-repudiation and identity verification.
Crucial for identity management.
Absolutely. And finally, FIPS 205, known as SLHDSA, which provides stateless hash-based signatures as a sort of fallback mechanism.
And the mandate for these new algorithms is echoing across the highest levels of government as well. The research highlights that the National Security Agency, the NSA, has unveiled their CNSA 2.0 quantum-resistant algorithm suite. They are explicitly mandating the transition to these specific lattice-based algorithms for all national security systems, military communications, and critical infrastructure.
It is arguably the largest cryptographic migration in the history of the internet. We are changing the tires on the car while driving on the highway.
Hmm.
But wait, let's play devil's advocate here for a second. Let's look at the architectural friction of this transition.
There's always friction.
If I'm listening to this and I manage a massive cloud deployment for, say, a multinational financial institution, do I just rip and replace my entire crypto infrastructure tomorrow? Do I just completely disable RSA and elliptic curve and forcefully turn on ML-Chem across all my load balancers and API gateways?
No, absolutely not. That would be an incredibly reckless architectural decision.
It sounds reckless.
The research is very clear on the dangers of a pure rip-and-replace strategy. We have to remember that while lattice-based algorithms have been scrutinized for years in academic circles, they are still relatively new compared to RSA, which has been battle-tested in the real world for decades.
True. RSA has survived every classical attack we could throw at it.
Exactly. What if these new lattice-based algorithms have a zero-day mathematical flaw that the academic community just hasn't discovered yet? What if next year a brilliant mathematician figures out a classical shortcut to solve the shortest vector problem in minutes?
Using a standard laptop.
Right. It's entirely possible.
That would be catastrophic. If you ripped and replaced everything, you would have migrated from a system that is vulnerable to future quantum computers straight into a system that is instantly vulnerable to today's classical computers. It would be a massive, self-inflicted breach.
Exactly the risk. And that is why the research unanimously points to hybrid cryptography as the only viable transition mechanism. Hybrid cryptography is the architectural bridge.
How does that bridge work?
It combines a proven, heavily tested classical algorithm, like elliptic curve Diffie-Hellman, with a new post-quantum algorithm, like ML-Chem.
It is the ultimate expression of defense in depth, but at the mathematical layer. Let's break down the mechanics of a hybrid TLS handshake for the engineers listening, because I know this adds significant overhead to the network.
It does add overhead, and that is part of the engineering challenge we have to face. In a hybrid key exchange, the client and the server don't just negotiate one mathematical problem, they perform both operations simultaneously.
Okay.
During the TLS handshake, the client sends both an ECDH public key and an ML-Chem public key in the client hello. The server responds with its own dual keys. They independently derive a shared secret using the classical method, and they derive a second shared secret using the quantum-safe lattice method.
So now they have two separate secrets.
Right. Finally, they use a key derivation function, or KDF, to mathematically smash both of those secrets together into a single, final, symmetric session key.
The logic there is absolutely brilliant, because you combine them. An attacker sitting on the backbone, tapping the fiber optic cable, would have to break both underlying algorithms to successfully derive the final session key.
Both of them, not just one.
If the CRQC quantum computer comes online in 2030, the classical elliptic curve part of the handshake is broken instantly by Shor's algorithm, but the lattice-based part holds strong, protecting the data.
Exactly.
Conversely, if a fatal mathematical flaw is found in the lattice-based ML-Chem algorithm tomorrow by some math prodigy, the classical ECC part still protects you against classical attacks. It completely bridges the gap without introducing new systemic risk into the environment.
It is an incredibly resilient design. However, as you alluded to, it is not without friction. Lattice-based public keys and ciphertexts are significantly larger in terms of byte size than elliptic curve keys.
How much larger are we talking?
Substantially. When you force a hybrid handshake, you are increasing the packet size of the initial TLS negotiation. In most standard web traffic, it's a blip. But in high-frequency trading environments, edge computing, or networks prone to UDP packet fragmentation, this added payload can introduce measurable latency.
It could push the packet over the maximum transmission unit size.
Exactly. It might require careful tuning of MTU sizes and network buffers across your entire infrastructure.
Which brings us perfectly to the cloud layer. Because if you are a cloud architect listening to this, you are probably sweating a little bit right now thinking about tuning MTU sizes across thousands of microservices and containers.
It's a daunting thought.
You're wondering, is my cloud provider actually ready to handle this?
Right.
Am I going to have to manually build this hybrid cryptographic routing myself in my code? Well, we dug deep into the research on how the big three AWS, Azure, and Google Cloud Platform are adapting.
And the silver lining in all of this research is that the major public cloud providers recognize the severity of the HNDL threat, and they are taking it incredibly seriously. They are actively absorbing the immense complexity of hybrid cryptography at the infrastructure layer so that their customers don't have to engineer it from scratch.
Which is a huge relief. Let's start by looking at Amazon Web Services.
AWS has been moving highly aggressively on the post-quantum front. They recognized early on the limitations of older libraries like OpenSSL, so they engineered and implemented their own cryptographic library called AWS-LC, which is a strictly FIPS 140-3 validated open-source library.
The scope of their rollout is really impressive. The research shows they are already pushing this across their most critical data handling services right now. We are talking about AWS Key Management Service, or KMS, AWS Certificate Manager, AWS Secrets Manager, their global CDN, CloudFront, and the AWS Transfer family.
All of the heavy hitters.
Right. All of these core services currently support hybrid post-quantum TLS key exchange.
And that translates to a massive operational benefit for the customer. It means that when your custom applications or microservices communicate with these AWS API endpoints, if your client SDK supports it, the TLS handshake securing that transit is actively dynamically combining classical ECDH with the post-quantum ML-Chem algorithm.
So AWS is silently protecting your data in transit from the harvest now, decrypt later threat right now, under the hood.
Yes. Without you having to rewrite your application's core logic, you just need to make sure your SDKs are updated.
Let's shift over to Microsoft Azure. How are they handling the transition? Because Microsoft operates in a vastly different ecosystem, heavily tied into enterprise operating systems, on-premise Active Directory, and legacy identity architectures.
Azure is taking a highly integrated operating system deep approach. They are embedding post-quantum cryptography via their proprietary SymCrypt cryptographic library. Right. This is the core mathematical engine used across the entire Windows OS, Azure infrastructure, and the massive Microsoft 365 SaaS environment. They are pushing these new capabilities through the standard Windows cryptography next-generation APIs, or CNG.
The research highlights specific Azure services that are leading the charge here. Azure Key Vault, which is really the heart of Azure's crypto shredding capability, now natively supports ML-Chem for quantum-resistant key encapsulation.
Which is great for data.
But what I found incredibly compelling in the research is how Microsoft Entra ID, which is formerly Azure AD, is handling identity. Entra is actively using hybrid cryptographic protocols to protect identity authentication flows and SAML and OIDC token signing.
That is a critical point to pause on, because if we only focus on encrypting data files and databases, we miss the broader threat model entirely. If a quantum computer can break the digital signatures used in public key infrastructure, it can forge an identity token.
Right. It could forge a JSON web token or a SAML assertion. Explain how that works.
Well, a SAML token is essentially just an XML document that says, hey, this user successfully authenticated. But to prevent tampering, that XML document is signed using an asymmetric key, usually RSA or ECC.
So the cloud provider verifies the signature before granting access.
Exactly. If an adversary has a CRQC, they can mathematically derive the private key used to sign those tokens. They could then craft a fake XML document asserting they're the global administrator of your cloud environment, sign it with the stolen private key, and the cloud provider will accept it as mathematically valid.
They don't even need to decrypt your data at that point. They just log in as the admin and hit the download button.
Precisely. By aggressively securing Entra ID token signing with hybrid PQC, Azure is locking down the identity plane, which is the true perimeter of the cloud.
That is a phenomenal insight. Identity is the new perimeter, and if the crypto securing the identity fails, the whole castle falls. You can crypto shred all you want, it won't matter. Finally, let's look at Google Cloud Platform. GCP has a long documented history of pushing cryptography forward, often ahead of industry standardization.
They really do. Google has always operated at a scale that forces them to innovate internally first. Their research reveals that Google Cloud has actually shifted their internal network traffic, the massive east-west traffic flowing between their data centers, to utilize ML-Chem key exchanges by default.
Between their own data centers?
Yes, they use a proprietary protocol called ALTS for this. So they are securing the backbone of their own infrastructure against quantum harvesting right now. For the services exposed to external customers, Cloud KMS and Cloud HSM have been upgraded to explicitly support the new NIST FIPS 203, 204, and 205 standards.
And they are heavily utilizing a framework called HPKE, or hybrid public key encryption, to seamlessly integrate these post-quantum mechanisms alongside classical cryptography within their APIs.
If we step back for a second and look at the aggregate actions of the big three, AWS, Azure, and GCP, what we are witnessing is really unprecedented in the history of tech.
They are quietly, methodically replacing the foundational bedrock of the Internet's security model.
All while the global economy continues to operate on top of it without interruption, They are upgrading the deepest layers of their cryptographic infrastructure so that when you, the architect, rely on their key management services for crypto shredding, you are inherently gaining a layer of quantum resistance.
Which brings us to the strategic action plan. Because relying entirely on the cloud provider to save you isn't a strategy, it's a hope.
Hope is not a strategy.
No, it's not. If you are listening to this, how do you architect your specific environment for the future right now? How do you prepare for Q-Day?
The first non-negotiable step is acknowledging that you cannot successfully implement crypto shredding, whether classical or post-quantum, without incredibly robust, mature key management lifecycle practices.
Cryptography is easy. Key management is brutally hard.
It really is. If you lose track of your key inventory, you inadvertently crypto shred your own production data and cause a massive outage. If you fail to destroy a key properly because a replica was left in a backup region somewhere, you fail your compliance audit and face massive GDPR fines.
And the research dives into a major architectural debate that every enterprise struggles with here. Where do the keys actually live? Do you use native cloud KMS, where the provider holds the keys on your behalf? Or do you enforce bring your own key, BYK, or hold your own key, HYOK architectures?
That's a huge debate.
A lot of organizations use cloud encryption gateways or cloud access security brokers, CASBs, to manage this. Time for a quick host note on this architectural friction. A cloud encryption gateway is a proxy appliance that sits between your on-premise network and the cloud provider. It tokenizes or encrypts sensitive data fields before the payload ever reaches the cloud.
The gateway approach is fascinating from a strict data sovereignty and compliance perspective. I mean, if you encrypt the data on-premise using a hardware security module you physically control, the cloud provider never sees the plaintext data.
They just see scrambled ciphertext.
Right. And more importantly, they never hold the encryption keys. If a nation-state subpoenas the cloud provider, all they get is ciphertext. If you need to crypto shred that data for a GDPR request, you destroy the key in your physical on-premise HSM.
The cloud data is instantly rendered useless.
Exactly. However, the architectural friction of this approach is immense.
It breaks almost every native cloud functionality. If you encrypt the data before it hits a cloud database, the database engine only sees ciphertext. You can no longer sort the data natively, you can no longer perform wildcard searches, you can't run native machine learning models or analytics against it.
You gain absolute cryptographic control, yes, but you sacrifice the primary benefits of using the cloud in the first place.
It is the ultimate trade-off between security sovereignty and operational functionality. But regardless of where your keys live, whether in an on-premise HSM or a native cloud KMS, the research emphasizes one critical operational practice that mitigates the HNDL threat right now: aggressive key rotation.
We really need to hammer this point home. Key rotation can no longer be viewed as just an annoying annual checkbox for your SOC2, ISO 27001, or PCI DSS audits.
It's not just compliance theater anymore.
No. The research makes it very clear that rotating your keys, preferably automatically and frequently, is fundamental to limiting your blast radius in a harvest now, decrypt later scenario.
We need to explain the mathematical connection there for the listeners, because a lot of people might not connect those dots. How exactly does frequent key rotation limit the quantum threat years down the line?
Okay, think about the timeline of the data harvesting. Let's say you use the exact same key encryption key to wrap your data payloads for 5 years straight. An adversary taps the fiber line and captures your encrypted traffic during that entire 5-year window.
They capture the handshake, they store the ciphertext.
Right. In 2030, they use a quantum computer to break that one single key encryption key. The moment they break that one key, they instantly decrypt 5 years worth of your highly sensitive data.
5 years of data gone in a flash. But if you rotate that encryption key every 30 days...
Exactly. If you rotate automatically every 30 days, breaking one key with a quantum computer only gives the adversary 30 days of data.
They would have to expend massive quantum computational resources running Shor's algorithm over and over again to break every single monthly key individually just to get the full 5 years of data.
Frequent key rotation drastically reduces the volume of data exposed. If a specific key is ever compromised mathematically, you are fundamentally shrinking the blast radius.
Which leads directly into a massive call to action for everyone listening today. You need to look at your cloud environments, your code repositories, and your deployment pipelines right now. Do you actually know where all your cryptographic keys are?
Most don't.
Have you conducted a comprehensive, automated cryptographic inventory across your entire enterprise? I guarantee most organizations haven't. and you cannot migrate to post-quantum cryptography if you don't know what classical cryptography you are currently running.
You can't fix what you can't see.
Exactly. You need to identify every instance of RSA, every hard-coded elliptic curve implementation in legacy apps, every self-signed certificate buried in your CI/CD pipelines. You need full visibility into your cryptographic debt before you can even begin to plan a migration to a hybrid ML-Chem architecture.
So let's synthesize this incredible journey we've been on today. The fundamental physical reality of cloud infrastructure makes traditional data deletion impossible.
Which forces the industry to rely on crypto shredding to achieve data sanitization and regulatory compliance.
Right. And crypto shredding relies entirely on the premise that our asymmetric encryption keys are computationally unbreakable.
But the impending arrival of quantum computers, specifically wielding Shor's algorithm, threatens to shatter those asymmetric keys, fueling massive harvest now, decrypt later intelligence-gathering tactics by nation-states.
Therefore, transitioning to hybrid post-quantum cryptography in your cloud key management services isn't a theoretical project for 2030. It is a critical imperative today to protect data with long-term confidentiality needs.
It is a phenomenal chain of architectural dependencies, and seeing how the pieces interlock really changes your perspective on risk. And it leaves us with a final, lingering, and frankly mind-bending question based on the context of all this research. We spent the last hour talking deeply about cloud databases, object storage, and key management systems. But think about decentralized ledgers and blockchain technology.
Oh, wow. That is a completely different architectural paradigm.
It really is. If quantum computers inevitably break the foundational digital signatures, the elliptic curve math, that historically secures every single transaction on a blockchain, what happens to the core philosophical concept of immutability?
That's a huge problem.
How do you retroactively update or crypto shred a distributed ledger that was architecturally designed at its core to never be altered when the cryptographic trust underpinning the entire chain is suddenly broken by a quantum computer? That is a massive paradigm shift, something for you to mull over as you audit your own environments.
That is a brilliant and daunting architectural problem to leave them with. Good luck sleeping tonight, everyone.
Thanks for tuning in to InfoSec Bytes. Keep exploring our 100-plus episodes on information security, AI, cloud, quantum, and cybersecurity incident root cause analysis. Please like, subscribe. We are on various platforms: Spotify, Apple Podcasts, YouTube, Amazon Music, and share to stay connected and keep your cyber defenses strong. See you in the next episode. Stay tuned.